later in the class, if they can, somebody over here can fix this projector. Uh, so in the interim, we will, oh, I just sent you all, an email as well. Monday, I have to be out of the office for just a little bit over an hour, between about 11 and noon, thereabouts. There's something, there's a job interview I have to, be at, not mine, somebody else's. Anyway, just let me know if that's an inconvenience, but I'll be around for the rest of my office hours. Okay, today. We're going to talk about one-to-one and onto functions, or what this notion means. Now, how many of you, maybe you don't remember what it is, but how many heard these notions, right? You've probably seen them at some point, maybe again in a pre-calc course where they talk about trig functions, or when they talk about inverse functions, back the old thing where you exchange y for x and solve for y. So let's get right into what this is. Definition. Suppose that f is a function from a to b. Number one, we say f is onto. Or subjective, if we want to show off our knowledge of Latin. If and only if the range of f. That is to say that, remember, B is just the codomain. That's just where the function is going to. If everything in B is covered, then we say that function is onto. Here's another way to say this. For all B and B, there exists A and A such that F of A everything in the codomain is covered. There is something in A that goes to it. We say that F is one-to-one. Injective. Yeah. If and only if. So that is to say, this, by the way, this characterization, f of x equals f of y implies x equals y. This is usually the easiest characterization to work with. You're going to prove something. But here's another way to do this. I'm going to write the contrapositive of the statement. Not this implies not that. This means that two different things in the domain have to go to two different places, right? In a certain sense. Example. So let's look at some examples. We'll start with something that might be a little bit more familiar. A function mod R be given by the way, what does this function look like? That is correct. This is a line. Slope M, intercept B, right? F of X is 1 to 1. If and only if anybody wants to guess what condition that we need here? Uh, we'll put this in a moment. What conditions some to? Gonna keep roll up into it. Well, again, as long as the line has non-zero slope, it is both 1 to 1 and on to. Let me tell you why, right? What does this mean? Two different x coordinates have to go to different y coordinates. This function, the way I've drawn it, is always increasing because what am I assuming? Increasing here means that m is what? Bigger than 0, right? If m was less than 0, it would go down to the right, right? But in any case, two different x coordinates go to two different y coordinates, right? Everybody's got a unique y coordinate corresponding to it. So it's 1 to 1. Okay, well, we'll stop there. Maybe talk about the next homework. The haunted classroom. Let's see. Almost there. Love that. Okay, so let me say a couple words about that. Next homework. And we'll get back to this. Let alpha and beta be real numbers and consider the totally ordered set Q less than or equal to, where less than or equal to is the standard notion of less than or equal to. And let B be the set of all rational numbers between alpha and beta, right? Q is strictly greater than alpha, less than or equal to beta. Show that the supremum of this exists if and only if beta is a rational number. Show that the infimum of this exists if and only if alpha is a rational number. Show that B has a maximum or greatest element if and only if the supreme B exists. And D, show that B has no minimum, period. It's got no smallest. 2, suppose we have functions f from A to B and g from B to C. Show that, and this is actually a useful exercise. This is a useful little theorem. Show that if the composition is onto, then the second one has to be onto. And show if the composition turns out to be 1 to 1, then the first one has to be 1 to 1. So if you compose two functions in a row, this is what the content of this is. This is F and this is G. And this is the whole thing. If you find the whole composition is onto, the second one must be onto. And if the whole composition is 1 to 1, the first one must be 1 to 1. Give an example where the composition is onto, but the first one is not. And also give an example in which the composition is 1 to 1, but the second one is not 1. Right? So this is a useful piece of information here. Number 3, and I'll give you 10 on this one too. Show that if f from A to B is both 1 to 1 and on to, show that f from A to B is both 1 to 1 and on to, if and only if there is a function going in the other direction, from B to A, such that when you compose G then F, when you do G then F, you get the identity on B, and if you do F then G, you get the identity on A. Right? One direction of this is very easy if you use the previous problem. Right? Number 4, suppose that F from A to B is a function and let SK be some collection of subsets of A. Show that if F is 1 to 1, then F of the intersection is equal to the intersection of F of the sets. And give an example in which this is not the case. I bet in your example, you should probably find a function that's not 1 to 1. And finally, and this is also, this one right here leads into what we're going to talk about after this section. We're going to start about counting, even counting the infinite. And so this is kind of an interesting result. Suppose you have two finite sets, right? Right. Here are two finite sets, and I hope that I'm right about this, but the chair's on this side of the room and the chair's on that side of the room. I think that these two sets have the same number of elements. Let's just pretend they do, right? Show that A and B are finite sets with precisely n elements. Suppose you have a function from A to B. Show that F is 1 to 1 if and only if F is onto. The fact that these two sets have the same number of elements is terribly important here, right? So if you have a set of 10 elements, if you say I've got a function from here to here that's 1 to 1, it's also onto. And if you say I've got a function from here to here that's onto, it also has to be 1 to 1. Here's the interesting twist of this. Show that if A and B are infinite sets, then neither of these implications hold, right? And in fact, see if you can even find an infinite set a single infinite set A, and two functions from A to A, such that the first one is 1 to 1, but not onto. And the second one is onto, but not 1 to 1. This is why infinite sets create a problem. If I have a function from a set of 50 things to a set of 50 things, if it's 1 to 1, it's onto. If it's onto, it's 1 to 1. But even if you have say a function from the natural numbers to the natural numbers, it can be 1 to 1 without being onto, and it can be onto without being 1 to 1. So those should be, I hope, some fun problems to think about. Okay, so as in the words of Snoop Dogg, back to the lecture at hand. So I claim that if this is 1 to 1, if and only if n is not 0, and so on. So let's prove this. Okay, the first thing I'm going to do is prove this function 1 to 1. Not 0. So let's go this way first. We want to show that if it's 1 to 1, then m is not 0. I'm going to do the contrapositive. Show m equals 0 implies f not 1 to 1. This is much easier to do, right? If m equals 0, then f of x equals b, right? And I don't know much, but that's a horizontal line, right? Check this out. Megan, give me two real numbers that are different. What is f of 2? It's b. What is f of 3? It is b. So f is not 1 to 1. because we have two different inputs giving the same output. Everybody okay with that? Ooh, see how contrapositive, that's much easier than trying to go directly. Let's go this way. Now we gotta show that if m is not zero, then f is 1 to 1. Okay, so here's my characterization of 1 to 1. F of x equals f of y, right? So let's suppose what does this mean? We'll just plug this into the formula. This means that mx plus b equals my plus b. Correct? Well, let's solve this. The first thing I can do is I can get rid of that pesky b by subtracting it from both sides. Correct? And then, let me be, let me be super careful about this here. I can certainly do this. Now, what do we know about m? So m times Fred is equal to 0, and m is not 0, so what conclusion must we come to? Fred must be 0. And there we go. Function is 1 to 1. I'm gonna finish this. Because I want you to see, this is a fairly elementary proof, but I want you to see that, how this works here. Let's go this way first. My claim is that if m is not 0, then this function has to be onto. Okay. What does it mean to be onto? It means anything in the codomain, in this case R, there has to be something that goes to it. So let's just pick. This function, the domain and the codomain are the same. Let R and R be anything you want. So what we have to do, so this actually should be part of your kind of scratch work, right? Let x equal would everybody agree that R minus B over M is an element of R? And the assumption here that M is not 0 is crucial, because otherwise this doesn't make sense at all. Notice that F of R minus B over M is M right, let's move from a function. This is R minus B plus B, which is R. So F is R. Everybody okay with it? We've shown that an arbitrary, I found the element. By the way, this is, I figured this out in my head. Notice how I didn't write down mx plus b equals r and solve for it. I did that in my head because structurally, I need to do that. I sort of, that was my scratch work that I did in my head, right? Let's do the other direction for this bit. smell coffee positive. It's got to make it easier. Let's try this. M equals 0 implies F is not on. In this case, again, can anybody name a real number that is not covered? How about anything except B? Right? Because look at the output. No matter what your input in, the output is just the number B. There is no X in R such that F of X is B plus 1. So F is not on. Everybody okay? So that's a pretty complete proof that the statement I made is correct. You all seem to be pretty familiar, or at least, you know, last a little nostalgic over the vertical line test, testing it something, right? Everybody was familiar with the circle, right? I drew a vertical line. Oops, not fun. Does anybody remember a test for one-to-oneness that you might have seen back in with pre-calc or when you looked at the inverse trig functions, like that? Yeah, there's a horizontal line test. How many of you have heard the horizontal line test? So here's another example. F is 1-to-1. If and only if no horizontal line meets graph of X in more than 1 point. So I didn't even say the function was continuous. And in fact, this will work more generally than this, as long as you're in some place where it makes sense to draw a horizontal line. I mean, it's really very too. Suppose F is 1-to-1. But Y B horizontal. We need to show that this thing can only hit the graph of F of X in one place, right? So this is not really part of my proof, but I just do this kind of visual aid. Suppose Y equals B intersects graph in at least 2 points. So X1 B and X2. So suppose this hits in at least 2 points. Let me fix my visual aid here. But again, this doesn't even have to be continuous. But suppose that it hits the graph. Notice that See, since x1 is not equal to x2, and f of x1 is f of x2, this implies f not 1 to 1, which is a combination. So what we've shown is if f is 1 to 1, then it can't hit no horizontal line can hit the graph of this in 2 points. So our conclusion is, so y equals b, that's bad, I'll say intersects. It intersects the graph of this function in, if it can't intersect, if it can't intersect it in 2 points, what can you conclude from that? It can only hit it in, what are my options now?
1 and 0.
1 and 0. Good. And that's what it says. It can't hit more than one, so it's got to hit in either 1 or 0 points. Let's go the other way. So suppose no horizontal line. You know, yeah, one. Suppose that is a true statement. Well, suppose f x1 will have x2. And let me call this something. I'll call this y. Suppose that f of x1 and f of x2 are the same. This means actually, let me not call it y, let's call this b. That'll be convenient. This means the horizontal line y equals b meets graph y equals f of x at points x1b and x2b. Right. Because when the point x1b is on the graph and the point x2b is on the graph, so y equals b hits it in these 2 points. But no horizontal line hits this graph at more than 1 point. So this implies that these are the same point. They can't be different, right? Hence, x1 is equal to x2. And so, f is 1 to 1. Let me ask you a question. When you talk about 1-to-1 functions back in the calculus days, this was usually a build-up to, it was usually kind of a build-up to inverse functions. Does anybody remember? That's kind of a terrible problem, right? Does anybody remember uh, how to get the graph of the inverse function from the original. I remember that little trick. That's right. You reflect, how many of you remember that you reflected about the line y equal x? Right. How many of you remember going through those crazy exercises back in the day when they would say, show that this function has an inverse and then find the inverse, right? What did you do in the first step of that problem? You took x and y and reversed the roles, right? That's exactly what you're doing when you're reflecting something over the line y equal x, is you interchange the roles of x and y. So if we were to do this, by the way, does everybody agree that this function is not one-to-one, right? Because look, there is a plethora of horizontal lines at this point. Here's the line y equals x. What would this look like if I reflect this around the line y equal x? It would be sort of a parabola that opens up the x-axis, right? So it looks something like this. Agree? This is why these things are related. See this horizontal line here? It violates the parabola y equal x squared being one-to-one. Agree? What happens if I see how I flip this parabola here around line y equal x? What happens to this horizontal line when I do this? It flips to a vertical line, doesn't it? Violation of one-to-one turns into violation of function. And that's why the horizontal line test works, and that's why it's connected to the notion of function. This is why often, this is also my warning to you, be a little bit careful about one-to-one. What one-to-one means, f of x and f of y are the same, then x has to be y, right? So that means if you have the outputs being equal, then the input had to be equal, right? What it means to be a function is given an input, there's only one place to take it, right? And so that's people often confuse the notion of function one-to-one. Just be careful, and if you ever get lost, just go back to the relation definition, which is always the best. Here's another one. Let me go through some examples here that I will not prove this completely, but you can do this as well. Look at this function here. I'm not going to go through a careful proof because I haven't developed the tools yet, but I think that probably intuitively you can do this. You might know what this looks like. That's not clear. But you could do it, right? You all are calculus scholars, you can do it. And in fact, if I wanted to figure out what this function looks like, what's the first thing that I might do? What does every 1060 student do when you give them a function like Pavlov's dog? It's like, ooh, I'm gonna take the derivative of that thing, right? What is the derivative of this? Do I agree with that? So this function actually is differentiable everywhere, so it's continuous everywhere. I guess I should have known that because it's polynomial. And that derivative is always greater than or equal to what? Well, that's certainly true, right? Always at least one. What can you say about this function if you were like analyzing the derivative for a sign chart? This baby is going up pretty steep. In fact, the slowest it ever goes up is a slope 1. So, I mean, more or less this thing's gonna look like this. It goes through -0, -2, And at zero, it's got slope one, but I mean, everywhere else it's like that. Can somebody explain why this is 1-to-1 and onto?
Given that the derivative never changes sign, it never like moves back on itself, therefore it never crosses the horizontal line, so it's plus the horizontal line and turn back down. That's
Real calculus over there, right? I mean, you're throwing rolls there and stuff. But yeah, he's right, right? The derivative's always positive, so it's always got to go up, can never loop down, right? And so notice this actually tells you this function is always increasing, right? So as you go from left to right, your y coordinate is going up. So there's no way that two inputs can give you the same, two different inputs can give you the same output. It's always going up. And it's onto. Because the limit of this as x goes to infinity is infinity. And the limit of this as x goes to negative infinity is negative infinity. And it's continuous. So every value has to be covered, right? That no matter what y coordinate you want, no matter what horizontal line you pick, there's some point where it will intersect this, right? So that can be sort of an improved test, right? If you have a continuous function, how do you know when it's 1-to-1 and onto? Here's an improved horizontal line test. See if you can prove this. See if I'm blowing smoke or if you can prove this. Every horizontal line hits the function in exactly 1 point. Right? Not never zero, but always 1 and only 1 point. Now functions can be weird. Let me get us warmed up with this. So you might think I'm having a stroke here, like this might look like a little bit of a non sequitur, but let me ask you this. Is this a function? Again, it's certainly a relation, right? It's a subset of Q cross Z. So just take your fraction AB and read the numerator, and that's going to be the Z. Right? This is relation. Is it function? Let's have a look, shall we?
No.
How many think it's a function? How many think it's not a function? You want to support your claim?
You could have, like, for instance, you could have F2A, which would be the same as F. It would be the function, the same argument as F, and infinity tips, like opposites.
Right. So let me give you a simple example. These two rational numbers are the same, right? So f of 1/2 is 1, which is f which is not equal to f of 2/4, which is 2. These two are the same input, right? Because 1/2 and 2/4 are the same. But if I write my fraction as this numerator, my output is 1, and with the same fraction, I get an output of 2. This is one of the things you have to consider with functions. This right here is a relation, but it's not a well-defined function. Because if you pick 3/6, right 1/2, and you pick 17/34, you will generate different outputs from the same input, right? Okay, now that I've got you worried about it, let me give you this function here. We're going to define F. This time to. Yeah, the natural numbers. But I'm gonna go through this exercise here of how to do it. So here's my rule. If Q is in the rational numbers, we write Q equals A over B. With GCD of AB equals 1. Now, this gets rid of this ambiguity here, right? Because remember how we screwed up the function by saying, well, I say 1/2 is 1/2, and my function or my relation gives me 1, and you say, no, 1/2 is 2/4, so the relation gives you 2. That's a problem. Did I completely solve the problem here? There's actually one more problem that's we can also solve. I'm an optimist by nature, so I didn't write anything negative down at first. But here's another problem. That's another ambiguity, right? Because 1/2 is -1/2. That function will still produce something different. So let me say this. Now, when everybody agree, now what I've done with those two conditions is that I've pigeonholed your fraction. There is only one way to write a fraction this way, right? If I demand that the fraction is reduced and the denominator is positive, I know the denominator can't be 0, but see, here, if I also demand the denominator is positive, I have to pick this one. I can't do this. Right? The numerator could be negative, but that will take care of the negative fraction. Right? I am going to find one of the weirdest functions you've ever seen. Don't bother trying to practice. And here A, B are under these conditions here. So I'll write my fraction in my neat form. I'm going to write this as 2 to the A, 3 to the B. If A is bigger than 0. I'm going to do 5 to the -A, 7 to the B, if A is less than 0. And so notice if A is negative, this will now be a positive power of 5. And by the way, I do love the reference to Jenny, but I should let you know that it is prime. All right. This is a function. And it's 1-to-1. So this is a weird function, right? Let's do a couple of tests on this, if you will. F of 1/2. Notice if I had written 2/4, I'd have to reduce it to 1/2 by my rule here. Right? Where does that go? Well, here it looks like A is positive, so this should go to 2 to the 1, 3 squared. This is 18. f of minus 1/3. Well, here a is negative, so that should be 5 to the minus minus 1. If I can emphasize this here, 5 to the 1, 7 to the 3, which is 17.1 or no, it's 75, doesn't it? I think that's right. And of course, f of 0 is 86753. None. Notice that this always gives you a natural number. Can anybody explain? Okay, first thing, why is this a function? Well, it's a function because because of these rules here. There's no ambiguity of what A and B are, right? So everything goes one place in that. The rule tells you exactly where to go, right? But why is it 1-to-1?
If A is greater than 0, then it's a one-to-one function. Using powers 2 and 3, and if A is less than 0, then use powers of 5 and 7, so they never overlap. Then if A is 0, then it's prime. Well, there's the outputs of prime.
Right. So suppose the first thing that I'd like to point out is they have to conform to the same rule, right? So suppose that A is positive and C is negative, right? That would mean that A is a product of a power of 2 and a power of 3, and B is a product of a power of 5 and a power of 7, right? Is it possible for those to be equal? No, because of the fundamental theorem of arithmetic, everything has a unique factorization in primes, right? And also, neither of these can be 8675309 unless they're 0, because this is also a prime, and this prime is not a power, it's not a power of 5 times the power of 7 or a power of 2 times the power of 3. That's why I picked different primes, so there's no overlap, right? Now let's suppose that A and C are both positive, right? This means that 2 to the A, 3 to the B is equal to 2 to the C, 3 to the D. Everybody agree with that? What does that mean? This means A equals C and B equals D by fundamental theorem of arithmetic. Right? The powers have to be the same because prime factorizations are unique. Right? So this is actually really cool. Go through the rest of the cases, see if you can verify this is 1-to-1. 1-to-1 functions generally indicate a smaller set. Which has more elements, this set or this set? The one on the left or the one on the right? The left. How many are on the left? How many elements in that set? How many elements here? 2. How many elements are over here? You know this is 1-to-1. You haven't even seen it. How do you know that it's 1-to-1 without being able to count? It just looks like more, right? And this is why. Bang, bang, there's a 1-to-1 function, right? I've got at least 2 over there. What if there's a 1-to-1 map display? This function tends to, this set tends to be smaller. Now you should notice this. This is a 1-to-1 function from the rationals into the natural numbers. So in a certain sense, the rationals are smaller than the natural numbers, aren't they? Not only that, I don't even cover all the natural numbers. There is no way to get an 11 from this formula. There's no way to get a 13. Most natural numbers are missing. You can't even get one of them. So put that in your pipe and smoke it. I hope that you can make it to the math club today, because it'll be an interesting talk on logic. Other than that, y'all have a good weekend, and we will see you on Monday.